What would happen if you fell into a black hole? Black holes are some of the most extreme and powerful objects in the universe. They have such strong gravity that not even light can escape from them. When we talk about falling into a black hole, we're discussing something incredibly intense and beyond our everyday experience. Though black holes are far away and not a danger to us, thinking about what happens inside them helps scientists learn more about the mysteries of space. So, let's explore what really goes on when you fall into a black hole. What is a black hole? Space and time are the two concepts that form the backdrop where everything in the universe happens. However, space isn't a static backdrop, and time doesn't work uniformly across the universe. Instead, they are both relative. This means that the presence of matter, like stars and planets, can distort space. When space gets bent, it influences how matter moves. This bending of space is what we experience as gravity. Black holes take this distortion to an extreme level. They are like trapdoors on the stage of the universe. These areas have so much mass concentrated in a small space that they create what could be termed a no-go zone. In these zones, the usual rules of space and time change dramatically. Most black holes are born from the death of very massive stars. When these gigantic stars reach the end of their lives, their cores collapse inward at incredible speeds, nearly a quarter of the speed of light. This implosion compresses the star's mass into an incredibly dense point, forming a black hole. For instance, a black hole with a mass 10 times that of our Sun would be just about 60 kilometers across, which is remarkably small compared to the vastness of space. If you tried to see a black hole, you wouldn't actually see anything. That's because the area under a black hole's influence is surrounded by what's called the event horizon. This event horizon acts like an invisible one-way boundary. Once anything crosses this boundary, it cannot return or send any information back to the outside world. This makes it impossible to see what a black hole looks like because not even light can escape from it to reach our eyes or telescopes. Despite their invisible nature, we can still detect black holes by observing their effects on nearby matter. Matter can orbit a black hole just as planets orbit the Sun. Near a black hole, you might find disks of matter swirling around this invisible point. This matter can speed up to incredible velocities, up to half the speed of light. The intense speed causes friction and collisions among particles, heating them up to temperatures as high as 1 billion degrees. This process turns the area around a black hole into one of the brightest spots in space, which is quite ironic given that the black hole itself is entirely dark. Effect of being close to a black hole. Approaching a black hole, you would experience one of the most bizarre phenomena in the universe due to the intense gravity at play. This gravity is so powerful that matter orbits the black hole and light does as well. If you were to hover just outside the event horizon in a region known as the photon sphere, you would encounter a surreal sight. Looking in any direction, you would end up seeing your own face. For example, looking straight ahead might shockingly reveal the back of your head. This happens because light reflecting off you curves around the black hole and comes back to your eyes. Gravity's influence near a black hole also extends to time itself. The closer you are to the strong gravitational pull of a black hole, the slower time moves for you compared to someone far away. From your perspective, events in the universe outside would seem to accelerate. However, from an outsider's view, your actions would appear to slow down dramatically. If you decided to leave the black hole and return to a distant point, you might discover that what felt like a short trip for you was actually many years or centuries for the rest of the universe, essentially putting you into a distant future where everyone you knew is long gone. But getting close to a black hole poses significant risks. One of the most dramatic is the danger of spaghettification. This gruesome fate occurs because the gravitational pull is stronger on parts of your body closer to the black hole. If your feet are nearer than your head, they will experience a stronger pull. This difference stretches you out, pulling you thinner and longer. As you move closer, this effect intensifies, eventually turning you into what resembles a thin stream of particles or plasma before you are consumed entirely. The risk of spaghettification varies with the size of the black hole. It's a particular hazard near smaller black holes, which have tighter gravitational gradients because of their smaller size. On the other hand, if you were approaching a supermassive black hole, like those found at the centers of galaxies, the gradient in gravitational pull is much gentler over human scales. Here, you might cross the event horizon without immediately experiencing spaghettification. From the outside, no one would ever see you cross the event horizon. You would seem to stop and slowly fade away as the light struggles harder to escape the black hole, eventually failing. What happens in the event horizon? Inside the event horizon of a black hole, space and time are altered in extreme ways. Here, the concept of real-time travel becomes feasible. Fortunately, because nothing can escape from within this boundary, the universe is protected from potential time travel paradoxes and disruptions that could arise if things were able to leave. Once you are inside the event horizon, survival becomes irrelevant because there is only one inevitable outcome: being pulled toward the center of the black hole. Inside this region, the structure of space-time is so distorted that every direction you could move in ultimately leads to the center. Ironically, to delay this inescapable fate, the best strategy would be to do absolutely nothing. At the core of the black hole lies the singularity, a point where all the matter that has ever fallen into the black hole is compressed to an infinitely small point. Here, the conventional laws of physics as we know them no longer apply. This transformation at the singularity means that black holes are characterized by only three properties: mass, spin, and electric charge. Each black hole is distinct only in its mass and the speed at which it spins, but beyond these traits, they are fundamentally identical. Black hole and singularity. The properties of singularities, much like the characteristics of fundamental particles, are useful descriptions on paper rather than precise reflections of reality. Our best theories, like general relativity, struggle to accurately depict what happens at the center of a black hole. Here, the curvature of space and density reach infinite values, leading to a breakdown in the traditional rules of physics. Essentially, the singularity, which lacks any surface or size, presents an anomaly similar to a divide-by-zero error in mathematical equations. This suggests that singularities might not actually exist in the form we currently imagine, or they could be something entirely different from our predictions. Our understanding of black holes and singularities is based on general relativity, our leading theory of spacetime. However, much of what we know, or think we know, about black holes comes from theoretical models that assume these black holes are not spinning. These models are favored because they simplify the complex mathematics involved. Yet in reality, most black holes are likely to be spinning. In fact, it is believed that nearly all black holes in the universe are spinning at incredible speeds, with some reaching up to 90% of the speed of light. This high rotation speed significantly alters the nature of the singularity, transforming it into a ring-shaped anomaly known as a ringularity. Black holes and dying universes. As the universe ages and moves toward its eventual demise, what happens to black holes? We're not entirely sure, but our current understanding of physics offers some intriguing possibilities, particularly concerning something called Hawking radiation. Hawking radiation arises from the principles of quantum field theory. According to this theory, the vacuum of space is not empty, but teems with quantum fluctuations. These fluctuations briefly produce pairs of particles and antiparticles, which typically annihilate each other almost instantly. However, near the event horizon of a black hole, something interesting occurs. Occasionally, one particle of the pair might fall into the black hole, preventing the usual annihilation. The other particle escapes as Hawking radiation. This escaped particle essentially takes away a tiny bit of the black hole's mass, because the energy to create this particle pair must come from somewhere, and in this scenario, it comes from the black hole itself. Over incredibly long periods, this process causes black holes to lose mass and eventually shrink. As the black hole diminishes, the rate of Hawking radiation increases. The process accelerates until the black hole emits a final burst of energy, similar to a high-energy explosion, and then nothing remains. Will we ever understand black holes? It's uncertain. Our current abilities only allow us to observe the external aspects of black holes, and likely, our existing theories do not accurately describe what happens inside them. However, this gap in our knowledge is a motivation for continued exploration and study. The fact that we don't know everything about black holes means there are still many mysteries to unravel and complex ideas to ponder. This is the essence of scientific inquiry, constantly questioning and seeking answers. And considering the immense lifespans of black holes, we have a vast amount of time to continue our investigations. Let us know your opinions on these massive black holes in the comments below. Don't forget to like this video and subscribe to our channel. Thanks for watching. Bye for now. Ding.